Hey everyone, so today I'll be going over the 2016 AP Physics 1 FRQ number 1. Feel free to just follow along, and I'll just be going over the solutions here. So, a wooden wheel of mass m consisting of a rim with spokes rolls down a ramp that makes an angle theta with the horizontal shown below. It looks like the ramp exerts a force of static friction on the wheel so that the wheel rolls without slipping. Okay. So the next question wants us to draw the free body diagrams where the dotted line represents the ramp. The length of the arrows do not have to represent the relative magnitudes. And we need to clearly state where each arrow is pointing away from and starting on. Alright, so let's just draw the arrows here. So the first arrow I'm going to draw is just the force of gravity, right? Because you know that if it has, if an object has mass, the force of gravity is going to act upon it. So the force of gravity will act straight down and point towards the center of the ground, which is going to be Fg. And let's see, what other forces do we have? We know there's going to be a force of static friction. So the force of static friction, because it's a rotating object, right, it's not going to be, say, like a block on a ramp where you can just, let's say this is the ramp and you have a block. You can't just draw this force of friction like this. That's just not going to cut it. So on this diagram, you're going to have to draw it where it makes contact. So that's going to be like right here, and we're going to call that the force of static friction. If it'll let me, right? All right. So I think there is another force here, and that's going to be, I think my force of static friction, that kind of looks weird. And draw it more parallel to the ground. All right, perfect. And now we want to draw the force normal, right? Because obviously if there's Fg, it's going to, the ground is going to exert a equal force back towards the object. And so Fg will just be through perpendicular like this, and we can call that force normal. And that should sum up our free body diagram. All right, let's move on. As the wheel rolls down the ramp, which force it causes a change in angular velocity? So a change in angular velocity of the wheel with respect to its center of mass. And we wants us to briefly explain our reasoning. All right, so let's just think about this. So a change in angular velocity, right? So we know change in angular velocity over time will give us angular acceleration. So if you think about it through a kinematics perspective, right? If your velocity is changing, it means there's going to be some sort of acceleration. And when it's a rotating object, right, angular velocity, change in angular velocity is going to mean there's an angular acceleration. And so because of that, we can observe our torque equations. So if we take our torque equations here, which is just sum of all the torque. Probably shouldn't write T like that. Let's write T like this. Sum of all the torque is equivalent to the distance from the radial line multiplied by the force and sine theta. And so now we can just use this equation and observe it for each of our following forces and see which one actually causes that angular velocity. So let's start with let's use Fg. So if we had Fg, so the torque for Fg would be the distance from the radial line, which in our case would be 0, right? Because distance from the center to where the force starts is 0, because it's right coming from the center. And so it doesn't matter what our force is at this point, or even the sine theta or the theta angle. That's just going to give us 0. So there's 0 torque coming from Fg, or a component of Fg. So now let's take a look at torque of force normal. So torque of force normal, the force starts out here, right? It's going to start right about there. That's kind of hard to see. But since it's starting on the surface and not on the center of rotation, we will have the R value that's not 0. So we have our force, and then sine theta. Theta is interesting here because the theta angle will be 180, right? Because the theta angle is measured in respect to the radial line. So because it's right on top of it, versus let's say static friction where it's a 90-degree angle, that's usually going to be 180 degrees. So sine of 180 would give us, sine of 180 would just be 0. So force normal ends up having 0 torque. Oops. Let's write this out completely. Sine of 180 would equal 0 because sine of 180 is 0. All right, so that leaves us with the force of static friction, right? And we can actually check here because the torque, force of static friction equals distance from the radial line. Is there a valid value? Yes, because it's not on the center of the wheel. So we have the R value, then the force, sine, and then theta. Like I said before, just mean 90 degrees. So that would be the force of static friction. So is the force of static friction. And this is my explanation. All right, let's move on. So for part B, it asks, for this ramp, angle, the force of friction exerted is less than the maximum possible static friction force. And instead, the magnitude of the force of static friction is 40% of the force in the opposite direction, and wants us to derive an expression for the linear acceleration of the wheel's center of mass in terms of those variables. All right, so I think what we should do is start off with Newton's second law. So sum of all the forces, let me just divide this so we don't get mixed up. So sum of all the forces is equivalent to ma, right? And if we're trying to find something for the linear acceleration, we can just divide both sides by mass, and we get sum of the forces over mass is equivalent to the linear acceleration. And so we know that sum of the forces in the positive direction will just be the component of Fg, which will be R F sine theta. And then we need to subtract 40% of the maximum because the force acting in the opposite direction of the force of static friction will just be the component of gravity. So we have 0.4 times R force sine theta. And this simplifies further down. Sum of the forces is mg times sine theta. And we can subtract 0.4 mg sine theta. And so now that we have sum of the forces here, we can plug it back into our equation. And so sum of the forces over the mass. So over the masses cancel bottom to top. And so now we're left with the simplified 0.6 mg sine theta. And that is equal to our linear acceleration. Let's move on. So the part C says in a second experiment on the same ramp, a block of ice, also with the same mass, is released from rest at the same instant the wheel is released, and it's from the same height. It slides down the ramp with negligible friction. So it asks which object, if either, reaches the bottom of the ramp with the greatest speed. So it wants us to first explain in terms of forces and then explain in terms of energy. So let's explain with forces first. So if the block, I think it would help if I drew a diagram. So this is the same ramp, and then we had our wheel here, and then we had our block. So if they are going down, right, our wheel, our block here doesn't have a force of friction, right? And they start at the same point. And our block does not have a component in sum of all the forces to oppose it. So if our original sum of all the forces was, let's say the gravity was mg sine theta, right? What you'll find is that this doesn't quite work out because mg sine theta minus whatever we have here, which we don't have anything, right? We don't have the force of friction. So we're going to be subtracting 0 versus the wheel where we had some of the forces equals mg sine theta. We had that static friction. And so we would have subtracted away 0.4 times mg sine theta. We saw how that simplified to this equation over here. So because of that, your sum of the forces, this value will be greater for the block. And we know that sum of the forces divided by mass will equal your acceleration. So if your value on top is greater and then your mass stays the same because it was stated, your acceleration will be the same as well. And so a greater acceleration for the block will mean a greater speed when it reaches the bottom because it's released at the same time. So greater acceleration, greater velocity at the bottom. So that'll be the block. And now it wants us to explain again in terms of energy. So I'm just going to cut this side off and look at these diagrams over here. So it starts at the same point and it's released from rest. And so in terms of energy, we're going to have the same gravitational potential energy, right? So the gravitational potential energy of the block is equivalent to the gravitational potential energy of this wheel. Now, because of that, they're going to be converted to kinetic energy, right? And the difference here lies in what kind of kinetic energy. So for the block, it's just all going to convert to kinetic energy translational. So it's going to be converted to translational kinetic energy. And this is going to result in pretty much linear speed, right? Because kinetic energy is the energy of motion. And so when it's translational, it's just linear. It's just linear and it's like displacement essentially. For the wheel, however, it's still going to all be converted to kinetic energy. However, it's going to be converted to two types of kinetic energy. There's going to be obviously the kinetic energy translational, which we said before would result in linear speed, but it's also going to be converted into the kinetic energy rotational. So rotational kinetic energy, and this is what actually causes, say that like wheel, let me draw a wheel real quick. That's what actually causes that rotation, right? And that's not exactly intertwined with causing linear speed, right? It can play a part in causing that speed. However, it's just not as much when you're talking about a pure linear speed. And so these energies have to be equal. And because of that, this translational speed for the wheel is going to be less than the translational kinetic energy for the block. And because of that, the block is going to have a greater speed at the bottom. So yeah, that does it for this video.